welcome back everyone. So today I'm going to be making a fairly, hopefully quick video on Weierstrass substitution. And Weierstrass substitution is kind of like an extension to use substitution in that, well, we make a substitution, but it seems kind of arbitrary, but we will see in an example that we will do that it actually really helps us out and simplifies the integral quite a bit whenever we have no other choices for integration techniques, right? And Weierstrass substitution, it's an advanced integration technique, so you use this, you don't frequently find this in a fundamental calculus course or calculus 2. Normally, of course, sometimes they might teach you, I don't know. So, well, let's get started. So the substitution that this concept is surrounded, is built on by, is substitution t. My marker is kind of getting ruined. T equals tangent of x over 2. And in this case, we're assuming that our integrals in terms of x. Not like, how Flan Level Maths does it. Like, he makes his integrals like in terms of smiley face or, I don't know, something really crazy. So, yeah. But that's just assume that normal people are integrating this stuff and we're doing it in terms of x. It could be in terms of t, in that case you would use probably a different variable for this. But the traditional variable is t, okay? And there are a few other bits of information that we need to that we're going to derive here in order to do the Weierstrass substitution. So firstly, we need sine of x. Then we need cosine of x. And we also need dx, of course. Okay, and these aren't that hard to find, okay? So let's get started. So to start off, it's a good idea to draw a right triangle, right? Because we're dealing with tangents, different trigonometric identities. So let's see what we can do here. Obviously, right triangle, and this case is our angle x over 2. Okay. Now, what is tangent of x over 2? Well, note that this is just t over 1, equivalently. So by the definition of tangent, this side, the opposite side of x over 2 is t, and the adjacent side is 1, because tangent is opposite over adjacent. Okay, and using Pythagorean theorem, we can easily find the hypotenuse, which is just 1 plus t squared. Okay, now this helps us in finding sine and cosine and dx in the end. Okay, well, let's see. So so sine is equivalently sine of x over 2 times 2, right? Because the 2's cancel. And this is the nice thing, right? Because there's a 2 here, and this is our angle. We can use the double angle formula for sine, and we'll do the same thing for cosine. And the nice thing is that we have our triangle here, and we know the trig identities for an angle of x over 2. We just found it here in our case. So recall that sine of 2 times some angle theta is nothing but 2 times sine of theta times cosine of theta. And also, we'll use this in a second, cosine of 2 theta is equivalent to cosine squared of theta minus sine squared of theta. Just pretty nice. Okay, so these will be helpful. And so now let's just split this up. This is basically just 2 sine of x over 2 times cosine of x over 2. And we can easily compute this. Sine of x over 2, that's just opposite over hypotenuse, right? And that's just going to be, so we have 2 times t over square root of 1 plus t squared. That's our sine. And then our cosine is just 1, it's adjacent over hypotenuse, 1 over, same thing, the hypotenuse, 1 plus t squared. Okay, and we can easily simplify this. We just get 2t over 1 plus t squared. Okay, so that's our sine. We finished that. And now for our cosine. Let's see. So we're going to use this identity, of course, this trigonometric identity or double angle formula for cosine. One of them at least. And this just becomes, and we can split this up in the same manner. We just get x over 2 times 2, which is just plugging this in. We just get cosine squared of x over 2 minus sine squared of x over 2. And we've already calculated sine and cosine of x over 2. This is just going to be, so cosine of x over 2 is just 1 over 1 plus t squared. So we square that, minus sine of x over 2, which is just t over 1 plus t squared. Okay, well, that's pretty easy to compute, right? We get the same denominator, naturally. So in the end, we just get 1 minus t squared over 1 plus t squared, which is pretty nice. And finally, for our dx, this doesn't really require much cleverness. We can basically refer to our original substitution, take the inverse tangent on both sides, and multiply by 2. So to do this, we can just get, well, we'll start down here because we haven't gotten it yet. So we note that by simplifying this, take the inverse tangent, multiply by 2, we get x equals 2 times tan inverse, or arctan, if you like, of t, right? Take the differential here, the derivative. We just get that dx, right? Take the derivative of that is equal to, remember, derivative of tangent is derivative, well, in general, derivative of tangent of x, tan inverse of x, is just going to be 1 plus x squared. And in this case, we're doing it in terms of t, so we're going to have our dt here, and we just have 1 plus t squared. Okay, so we've got all our bits of information. Now let's take a look at our example. Now, we're just going to be doing one example for now. I might make another video where we do a few more, potentially, but we'll see. So we'll take a look at this example. So, what is the integral of 1 over 1 plus cosecant of x dx? So, you can just try our basic techniques. Nothing would work here, right? So why don't we try Weierstrass substitution? Anytime you see something with sines or cosines, then that's always a hint that you might be able to, it might be useful to use Weierstrass substitution here. But you should try everything else first, or at least look through it. Okay, so notice that cosecant of x is nothing but 1 over sine, right? So this is nothing but the integral of 1 over 1 plus 1 over sine x dx. And now let's make our substitutions. Substituting our sine, we get 2t plus 1, 2 over t, 2t over 1 plus t squared. And then obviously we need to substitute our dx as well. And many cases you won't have to use all of your information given. For example, we don't have to use cosine in this case. It's not going to be useful here. We only have our sine. This is a relatively simple example, so that's why. And so substituting we get, okay, so sine of x, we're taking the reciprocal of that, so we get the integral of 1 over 1 plus, so take the reciprocal of this, 1 plus t squared over 2t times dx, which is just, well, 2 over 1 plus t squared dt. Okay, probably useful to get a common denominator here, so let's do that. And take the reciprocal of that, we could do that in our heads. We just get the integral, take the 2 out by the way. Actually, we'll leave that in there for now, just to not do too many things at once. And our denominator will be, well, we're not going to distribute it yet. Well, we can just distribute it, right? We're just going to get t squared plus 2t plus 1 times 1 plus t squared. We're directly foiling these out. And then we have our 4t on the top, dt. And this looks very much like something we should use partial fractions on, partial fraction decomposition. Now, I haven't done a video on that. I might do one in the future, possibly the next video, but we're just going to do that right now. Okay? And we obviously, since our denominator is greater than our numerator, so we can't do any nice division here. Just to make sure I got that right. Yeah, it looks good. So factoring this is a perfect square, or it's the product of 2 equivalent binomials, being t plus 1 squared, so we just get that this is equivalent to taking out the 4 as well. We get t over t plus 1 squared times 1 plus t squared dt. So we just have to work out this integral. This might be a bit tedious, but let's try it out. So, doing our partial fraction decomposition, we want, okay, we're kind of running out of space here, but basically we need t over t plus 1 squared. Right now I'm just setting it up. We want this to equal a sum of the following partial fractions. So we just get a over t plus 1 plus b over t plus 1 all squared plus cx plus d over 1 plus t squared. Okay, I'm not going to use the cover-up method here. I don't really like it, personally, but you can use it if you want. So let's do this. And we need, so if we multiply everything by this, we're going to need, obviously by the greatest common, the GCD of these polynomials, which is just this here, t plus 1 squared, all squared, times 1 plus t squared. So all in all, from this we can extrapolate that we need, this implies that t must equal, okay, so here we're just going to end up with a factor of 1 plus t squared times t plus 1 times a. Here, that's going to cancel, so we're just going to end up with factor of t, okay, I'm going to make this good here, 1 plus t squared b plus, and here this part needs to be, so we're just going to get, yeah, so this is just going to be t plus 1 squared times cx plus d. Okay, so, well, this looks kind of ugly right now, obviously. Okay, so what can we do here? So whenever you're in situations like these, you want to find values that will cancel out a few terms. So for example, for t equals -1, let's let t equal -1. We would need, so that would imply that, I don't know what that notation was there, but whatever. That would imply that we have -1 must equal. Okay, so what do we get here? We just get, this entire term goes to 0. This term doesn't go away. We get, here we just get 2b. And it seems like this will go to 0 as well. because we're letting t equal -1. It's important that we don't make a mistake here, of course. Yeah, that goes to 0. So we can direct, which is good. So now we can solve for b. So we get that b equals -1. Okay, good. So let's see, what other term could we potentially cancel out? Well, let's see. So, yeah, okay. By the way, this should be a t. That would be much better. Well, we need that to be a t, of course. It's a polynomial in terms of t. Okay, so b equals -1, which is good. I actually haven't really done this by hand, so already I haven't done the I haven't done this integral by hand yet, essentially. So yeah, so since these, it doesn't look like we can do much because okay. So it seems like we're just gonna have to get some. We're just gonna have to do some, manual integration, right? Or sorry, not integration. We're just gonna have to put this into a polynomial, because from this we pretty much just get that. Well, so this becomes negative. We want to add that to both sides. We get t squared plus t plus 1. We need that, so make sure I did that correctly, because b equals negative, what am I doing? B equals -1/2. Okay, so that's probably not the best idea. Yeah, I mean, yeah, we should do this. Yeah, so we just have 1/2 t squared plus t plus 1/2, obviously, and this is just nothing but what we have here. So 1 plus t squared times t plus 1 a plus t plus 1 squared ct plus d. Okay. And now we could distribute here, but that wouldn't be very nice, of course. So it would be good to think of something that would simplify this a lot. Let's see. Okay. So normally what you would do is you would just make this into a polynomial, and you would set the coefficients here equal to each other. So it looks like that's what we're gonna have to do, which is fine. So let's do that. So, and I'm obviously running out of space. Hopefully you can see this part of the board. Yeah. Okay. So this polynomial becomes, well, okay, let's FOIL out. We get t plus 1 plus t cubed plus t squared, and then obviously, well, actually all of these terms are multiplied by a, so we have a, sorry about my messy handwriting right now, and then plus, square that. Okay, that's going to be pretty tedious, but oh well. T squared plus 2t plus 1 times ct plus d, and this is equal to just this part. Let's focus on that. I'm very much running out of space. Let's see if I can potentially make this a bit better. So we have, this just becomes ct cubed, just focusing on that part, plus dt squared plus 2ct squared plus 2dt plus ct plus d, it looks like. Looks like that's what we get. Okay. So now, then we want to just get rid of this arrow. I'm going to clear some space. It's times like these when, being able to edit would be very useful. So I'm just going to get rid of all of that. Okay, that's going to be helpful, so. Okay. So in the end, we should just get AT plus A plus AT cubed plus AT squared plus, and we still need to combine like terms, CT cubed plus DT squared plus 2CT squared plus 2DT plus CT plus D. Hopefully I did that correctly. Okay, and of course we need to still combine like terms. And this just becomes, so this must be, so this must obviously be 1/2 t squared plus t plus 1/2. So yeah, let's combine like terms. We have a plus c t cubed, so we can get rid of that, plus a plus 2c plus d should be t squared plus this. Okay, so this is getting very disorienting, so here we just get a plus c plus 2d t, okay, plus, and then we just have a plus d, right? Okay, so finally, assuming I did that correctly, which is, to be honest, a bit unlikely, but we'll see about that. Okay, so from this we can essentially just extrapolate that, well, a plus c must equal 0, right? Then we have a plus 2c plus d must equal 1/2. Then we have a plus c plus 2d must equal, well, this is the coefficient of t, that must equal 1. And then finally a plus d must equal, what do we get? Should be 1/2. Okay, so let's see what we can get from this. So we can directly eliminate a portion of these two equations. So we can subtract this a plus d equals 1/2 and a plus 2c plus d equals 1/2, and we can cancel the a and d. So we're left with 2c equals 0, thus c equals 0. Okay. And we can plug c into this one, and this one, and we also get that a equals 0, and d equals 0, which is interesting. So a equals 0, so if we plug in c here, yep, d should be equal to 0. Oh, that's an A. So we know that, make sure that I wrote this correctly. So A equals 0 here, C equals 0, D is actually equal to 1/2. So D is 1/2. And okay, good. And is there anything we're still missing? And we already know B. B is just negative 1/2. Okay, so we have everything, which is good. Now we just plug it back into our partial fraction decomposition. Okay, so A is 0, so this term cancels. Let's see what else is 0. C is 0. So we're just left with 1.